So in the rate-based calculation, we will design and specify the column internals. So add new. So start stage 1, end stage 10. Choose rating, packed, choose say Melapack. It is a structured packing. Let them be default only. And let us choose a section height of 15 meter high column, and say a diameter of 2.5 meter diameter. And then we will go to the rate-based modeling, and there first we have to change it to the rate-based. Instead of equilibrium we have to use rate-based, and then go to the rate-based setup, go to the section and tick over here. So it will perform rate-based calculation, and in this case you find the hold up through correlation. So you can just go over here and remove the hold ups. It won't be required in this case, and go back to the rate based setup and go to the design, and you have to choose a design mode to calculate the column diameter. What will be the base flood? Okay, so we'll put it at 9th stage. So we will calculate the column diameter for which there will be 80% of flooding. With that, we will run our simulation. Okay, let us see whether it converges. So okay, so there is a problem over here. Let us see what is the problem. The limiting stage is 8 and the percent approach flooding is 46. So we will reduce the column diameter. Okay. Put it as 2.4. Now let us run it once again. Yeah, now it is converged. Let us see the hydraulics. We will check it in the column internals. So these are the hydraulic plot. Okay. So all stages are given over here. So the operating point should remain within this range, and the entire column should be blue. That means the vapor and liquid, everything is in good condition. and the limiting stage is 4 and approach to flood is 54. So we can still reduce the diameter from 2.4 to 2 and try. Okay, because as per the result, it says that the calculated diameter in rate-based design, it is 1.95. Okay, so if we take a 2-meter diameter column, then also it will not cross 80% of flooding. So 2-meter diameter is okay. Now we are not going to change the diameter for now because we are going to bring in some recycle. So we do not know what will be the effect of the recycle, how much water will come, how much lean amine will come in addition to whatever we are feeding. So there we may need a higher diameter column. So let us not disturb the column diameter right now. We'll change at the end if we need at that time. Okay, so we will follow our next stage. So what is the next stage? The CO2 rich amine is fed to the stripper with following specification. So stripper specification has been given. So we shall bring in one rat frac column and we will use this particular icon, and this icon, let us increase the size a bit. Okay, and we shall feed in this connection over here. Okay, and before that we have to pass it through a heater because we have to preheat this liquid. Okay, so let us use this heater. So this one will connect here first, and then we shall, okay, for the timing let us switch it off, and then we connect this one with this. Okay, now name it as stripper feed. For the specification of stripper, it has 10 stages, so let us open it. It has 10 stages. Feed stage is 2, and it has partial vapor liquid condenser. So partial vapor liquid condenser, reflux ratio 0.35, reboiler duty 0.02. So this is 0.35, reboiler duty is 0.02 gigawatt, and the stream, the feed stream at second stage, okay, so there will be 2 outlets. One is the vapor distillate, that is CO2 out, and there will be another outlet like this. Okay, and this is the bottom outlet, right? So basically we have to set the pressure over here at 1 atmosphere, and the condenser temperature is given over here. It is 40 degrees centigrade, so we place it 40. Okay, rename it. let us rename it as stripper and do not hide it. Keep it over here. Rename it as CO2. Okay. And then what else do we have to? Oh, B3, this one. So this one, let us open, and okay, one thing you must remember that in future we shall take the heat from this line, okay? But for the time being, we are not using the recycle, so we shall use an independent heater or self-sustaining heater, okay? So for that, we have to provide some kind of temperature information. Let us take it as 90 degrees centigrade. And this is also a wild guess. I do not know whether this will be sufficient. Let us try. Okay. And if this is not sufficient, we have to change it because it is anyway a simulation. We have to do some trial and error. And then we can run the simulation. Mind that we are using it in the equilibrium mode. Okay. Okay, so the results are available. So it has run. Okay, it has run. So what is the result over here? So you can check what is the result. So CO2 and S3, these two things you can check. CO2, S3, and this one you can just rename it as lean amine recycle. Okay. So we shall see the flow rates of components in these three streams: 2 distillate, CO2 and S3, and 1 bottom flow rate, lean amine R. So just see the results. So this is lean amine R, this is CO2, and this is S3, right? Yeah. See, the temperature of lean amine R is 105. So this is the reboiler duty, which is increasing the temperature from 90 degree to 105 degrees centigrade. But what are the mass flow rates? You can see S3 contains mostly water. So this one we are going to recycle over there. On the other hand, much of the PZ, MDA, these are in the lean amine stream. Okay. So we shall delete this stream and connect this one with this distillate, as if the distillate from the stripper is fed into the absorber in a recycle mode. Okay, let us run this simulation and see whether it converges. So let us run it. Yeah, it converges. So the simple recycle converges without any problem. And now we will use another heater like this over here, connect this lean amine stream to that heater to cool down the temperature of that stream before it is added to the lean amine section. Okay. So let us use another heater over here. It will be cooler rather. So let us choose this one. Okay. Yeah. So we shall connect this one to this, and we have to recycle it to this, and we will put a mixer over here. This one will keep over here, and this lineamine stream we shall connect it with this point, and there will be a makeup stream, something like this. Okay, so this is the makeup stream, and another stream will be connected like this. Okay, so then the entire flow sheet will be completed. For the time being, let us keep it open like this. So this one we call recycle stream, and we will need a charge balance over here because we are using lot of electrolyte, right? So there will be a charge balance problem, I believe. So it is customary to use a charge balance block in the entire flow sheet somewhere so that the charge balance is taken care of. Charge balance will be there in the manipulator block. So put the charge balance over here. Connect this stream with the charge balance like this, and the outlet of the charge balance should come over here. Okay, now this stream we can hide the ID. Okay, so this is the entire operation that we will do, and the lineamine temperature is 40 degrees. So the lineamine recycle will be cooled down to 40 degrees from 104.3 degrees centigrade to 40 degrees centigrade. So here we shall use 40 degrees centigrade at 1 atmosphere. So this is one heater, or cooler rather, which will step down the temperature from 104.3 degrees centigrade to 40 degrees centigrade. Okay, let us keep the makeup fluid same as the lineamine fluid because we are not adding anything. So for the time being, let the makeup fluid be 40 degrees centigrade at 1 atmosphere. The mass flow rate may be 40 kg per second. The mass fraction MD is 0.45, PZ is 0.05, and water is 0.5. Okay, that's how the makeup fluid is made. Okay, now run it once again. There should not be any problem in convergence because this part already has been converged, so only a few peripheral things that we have added, nothing else. Yes, it has converged without any issue. Now we will convert this stripper into rate-based calculation. Okay, so one more thing, we have not added the reactions to it, right? So first we have to add the reactions So go to the stripper setup, make it red based, go to the reaction, add 1 to 10 stages, reaction R1, then come to the column internals, add 1 column internal, add new section from stage 2 to 9, because here it is a stripper, right? It is a stripper. So in the stripper, stage 1 is condenser and stage 10 will be the reboiler. So only in between 2 to 9 we can put on the packing material. So that's exactly what we are doing right here. Rating packed, just like before we are choosing a Mela pack. And take 15 meter high and 2.4 meter diameter as before. We'll begin with this and let us see whether it converges. Otherwise we have to change. Go to the rate based calculation, tick the rate based calculation and tick the design mode. I don't know where it will be put, but just put it at second base stage, because at that stage we are feeding in the stripper feed. Okay, so that's how it is to be done. Yeah, so now run it. Okay, so there is a problem, I believe. Okay, so I don't find any error over here. I mean, only 8 warnings, no simulation error, right? So no simulation error. Let me check why it is said input changed. No, there is no issues over here. So I believe we can rerun it. Okay. Okay, let me see how the convergence can be achieved. We have to make certain trial and errors over here. Okay, so let me try. It may take some time. Okay, so finally I have been able to converge the solution. So I can show you. So you can see results available. We are able to converge the solution. Now I had to make certain changes here and there in between. I will show in short so that you can understand. Here I had to go to the column internals, and there I had chosen a diameter of 2 meter instead of 2.4, and that gave me the hydraulic plot in this fashion. Okay, so operating point is within this range, and the column hydraulics is something like this. At limiting stage of 9, there is a 76.24% of flooding, so it is not going above 80% limit. So, and in fact this matches with the results also. You can see the results. Okay, so they have not calculated it. I will recalculate with that. So what I'll do, I will recalculate the design mode at base stage of, I think it is 5 or 4. I forgot. Let me check it once again. Column hydraulics. Yeah, limiting stage 9. So we have to go back over here. And limiting stage 9. Right. So run it once again. And check the results. Yeah, it says 1.95 meter is the calculated diameter with 80% flooding limit for the 9th stage. Okay. Column diameter I have taken 2 meters, so it is not crossing the 80%. In fact, it is limited at 76 point something percentage. Okay, 76.2418 percentage. So it is okay, right? So this stripper diameter is okay. So in short, we are able to perform the open loop simulation up to this point. Now we have to add in this line with this particular mixer so that the loop is complete. Okay, we can say the lean amine, which is carrying 39.75 kg of material, that will be sent to this string. Okay,